Strata has in the past focused on sort of fire and fuels effects. Last year we also, or I guess this year we also had an igniting exchange meeting, which was a rather large combination meeting between us and the Northeastern Forest Fire Protection Compact. It was really well attended, and I think we really served the missions of both organizations at that meeting. Another thing that we really work on, or this is sort of Inga's realm, is to try to take some sort of peer-reviewed literature, sort of the primary lit, and to condense that down, or boil it down really to a couple key points and a one-page sort of summary of that work that we think that really sort of helps the managers wade through sort of the very dense things that are out there. We also have a sort of quarterly newsletter that has a lot of different information from our region. It's put out. And if you would like to subscribe to our group, just shoot one of us an email after this, or go to the NAFC website and there's a subscribe link. We try not to really blast too much stuff out there. We also have a social media presence, and all of these webinars and all the webinars in the past that we've had are actually archived and provided through YouTube on our website. All right, so today we have sort of the next episode of a webinar series that we are putting on this spring and summer, and it's really focused around a large project that many of us are collaborating on in the region, really taking a fundamental look at the physical processes behind wildland fire behavior and spread. For our region, this is particularly topical because it's focused on the fire that we use. We're focused sort of on low-intensity fire. Prescribed fire is typically low intensity in most of the country, and so that sort of has things that happen at different scales. And so we're trying to figure out how we can best move between sort of the laboratory scale and the field scale to investigate things that are relevant for fire behavior modeling. So without further ado, I want to introduce, we have sort of a dual talk today. It's going to be a collaboration between Albert Simeoni from Worcester Polytechnic Institute and S.K. Im from the University of Notre Dame. Albert has a pretty long, well, not that long yet, I guess, but a pretty storied career. He's been in a bunch of different places through his career, including Worcester Polytech, where he's been for a while now. And he came there from the University of Edinburgh in the UK. And he has also a bunch of experience on the fire line. And so that's one of the things that make Albert really special, I guess, in the fire science community, is that he has sort of ground experience on the line, and he also has wonderful training in physics, and is an engineer, and so there's not very many folks that sort of bridge those two gaps. And so our other presenter today, Seong-kyun, has his PhD in mechanical engineering from Stanford University, and we sort of sucked SK into this wildfire stuff. He's a mechanical engineer that looks a lot at combustion and flow diagnostics. And so the wildland fire game is a little bit new to him, but we've sort of pulled him in as sort of a really awesome specialist on this project. And so without further ado, Albert, it's all yours.
Thank you. I don't see the
there, Albert?
For the moment. Yes, I'm here. Can you hear me?
Yes.
So I don't see the presentation for the moment. I just see a white screen.
Okay, let's see. SK, can you see the presentation?
Yes, I do. So I can start while Albert is working on pulling up the presentation slide online.
Okay, I'm guessing, Albert, that it's a sort of data transmission issue. So maybe you can trust to sort of advance through the slides if you want to just dive into the presentation.
Okay. So I'm putting the presentation on my side very quickly. Oh, I see it. Okay. So basically in the frame of the startup project that Nick was mentioning, and thank you, Nick, for the introduction. We are developing a mid-scale portable wind tunnel for laboratory and field experiments, and and SK will detail what the wind tunnel is and how we used it for the moment. What I want to tell you about is why are we doing that? So can we go to the next slide? Yes. Okay. Thank you. So on this project, of course, we have a large team which is looking at different aspects of the fire. So we go from the very small scale, which is looking at the combustion of the fuel and how it burns at small scale, to the spread of smoke and everything in the middle. And for this project, especially Giovanni Di Cristina, who is a PhD student at Notre with SK, is using the wind tunnel, and so there is a special thanks to him. Next slide. So that's the presentation of the project in general, and so we're really trying here to improve numerical modeling because our vision for this project is that if we can improve the numerical modeling of fire behavior, so basically if we have cutting edge physical fire spread models, it can be used to support managers and to make predictions on the fire behavior and on different scenarios for prescribed burns. So at the core, we have the numerical modeling, but as fire is happening at different scales, and more about that in a few slides, we need to cover these scales. So we go from the small scale, which is square number B, to the mid scale, to the field scale, through small scale field experiments and operational burn observations. And this is what we hope is a virtual loop which will inform numerical modeling at every stages. And so the wind tunnel and the presentation of today is for the mid-scale laboratory experiments. Next slide. So the motivation for the whole study. So if you're looking at wine on fire, and we can apply that to prescribe burns too, it's a very complex phenomenon. And whatever aspect of wine on fire you want to describe, you have to be pretty inclusive if you want to do good predictions under different scenarios. We went back. So, SK, can you move forward one slide?
So we are on slide 4, motivation. Do you want to go next one?
No, I see that I'm going backwards.
No, I
okay.
See it.
Let me
slide 4.
Let me pull my presentation. So at least I will see what's happening. So slide 4, we say. So if you want to describe wine on fire, you have to look at the different physical phenomena and chemical phenomena which are happening at different scale. So we can start by the bottom and look at combustion, which is basically chemical reactions, and then to spread, and it happens through the pyrolysis, which is basically the thermal degradation of the fuel, which is throwing flammable gases in the air or in the gas phase, and it's fueling the flames. And then you have the heat transfer, which is spreading the fire. So ahead of the fire front, you have radiation, which is like solar radiation, a long distance effect by electromagnetic waves, or you have convection, which is the motion of the hot gases. And for instance, for a fire to spread from the surface to the crown of the fire of the trees, convection is a very important phenomenon. And then you have on the far right smoldering, which is basically when the flames are gone, the fuel remains in the form of char, and in contact with the oxygen, like the embers in a chimney, it will smolder and burn in these as embers for quite a long time. And then all these combustion, whichever flame or smoldering combustion, is creating emissions and smoke, and you have, if you want to look at the smoke dispersion or at the health effect, you have to look at the atmospheric dispersion of these gases and even the particles. And in addition to that, a real risk of escape for prescribed burn, or a real risk of impact on a wildland fire for structures, is firebrand transport. So the firebrands can do spot ignition, or if it's a firebrand shower at short distance, can ignite structures. So this whole phenomena that I described involved several physical chemical mechanisms that we have to describe in the models. Next slide. So one of the critical aspects of wildland fires is that the things happen at very, very different scale. So if you're looking at the inside of the rectangle, you go from the reaction, which is at the scale of a micro or millimeter, and you go up to the atmospheric scale, which is at the scale of hundreds of kilometers. So we have, in a way, to cover all of that, and at least to describe prescribed burns, we have to cover the 4 first squares. Then if you want to cover the atmospheric dispersion and large fire behavior, then you have to cover the 2 last squares. So that's really a problem. And also, at the end of the day, if you're looking at the dispersion of smoke, it's heavily dependent on the chemical reactions. So all the scales are linked. And on the other side, if you're looking at the effect of wind or mass fires, when we say that the fire is creating its own wind, then you're going the other way from the atmospheric scale to the reaction scale, when the wind is fanning the flames or the embers. So really, one of the big challenges of this problem is to cover the different scales. And to do so, you cannot describe everything at molecular level. You cannot go to the reaction and say, I'm going to track every molecule which is reacting in this thing and how it transported or how the heat is transported. So you have to make assumptions, and you have to make assumptions in the way you describe how one scale influences the other. Next slide. So here we're talking about CFD-based detailed physical models. And what are they? Basically, they are models which can describe the fire in 3 dimensions mainly. That's what we are looking for our application, because we need to track the fire front, but also the smoke. So here what you're seeing is a simulation with WFDS, the Wildland Urban Interface Fire Dynamics Simulator. And they really describe in a very fine way the flow and the combustion reactions and the transport of smoke at the scale at least of the fire front. If you want to go beyond that, you need to couple these CFD models with atmospheric models like the models used for weather forecast. So at the stage in which we are, these models are still what I call models of knowledge. It's basically we throw into the model, excuse me, or basically we agglomerate all the knowledge we have about this phenomenon, and we look if we can provide simulations which are describing more or less the fire behavior. So all of that to say that they're very complex, they have a lot of parameters, but they are still in a way not validated and not designed to work in the field yet. Some applications were made where on limited basis they were able to reproduce some field experiments for the moment. One was done by most of the people in the Solar project in the Pine Barrens. Others were done for fire spreading in grasslands in Australia. But the problem we have for the moment is that we're not sure that we are really transferring the information from the small-scale combustion to the large scale of the fire front. And so the big question for us is, do we capture or can we capture the physics properly? And what does it mean, in a sense, is where do we make the cutoff? Because as I said before, we cannot write every molecule, but we have to be detailed enough to describe the fire spread, but let's say do the right approximations so the model is still able to work on a computer and will not take for ages to run. So how much physics is enough is a big problem, and because fire is so complex and made of so many coupled interactions, we need the support of experiments to validate every step of improvement of the model at every scale. So we do very small scale experiments, and it will be presented another time. We do vegetation modeling. We try to understand how even the vegetation is becoming flammable, how it burns. We do fire spread experiments in the laboratory, in the wind tunnel, and that's what I will mention in the remainder of my talk, and also in the field. And we are trying to track every time that we are capturing the right physics, and that's no small endeavor. Next slide. So basically, in the model, to be a bit more precise, if you're looking at the gas phase, which is basically the air and everything which is in the air, including the flames and the combustion reaction and the soot and the smoke, and you're looking at the solid phase, which is basically the fuel, so the vegetation, you have a lot of things to take into account. And one of the important things which makes wildfires and wildfire science so special is the coupling between the two different phases through how vegetation burns. So you transfer mass, basically you transfer flammable gases, which are made of broken down molecules of vegetation, which are going into the air and basically fueling the flames. You transfer heat from the gas phase to the solid phase, for instance, the radiation and the convection from the flames to the unburned fuel to spread the fire. And you transfer momentum, which is basically the flow and the fire and the smoke plumes. So everything is extremely coupled, and one of the critical aspects is to represent these transfers. So this is what's in red in this slide. Next slide. And so in the models, we represent what we call a multi-phase model. Is basically that every single small element or cell that is described in our model, because when we make a simulation, we divide our whole physical domain in small cells, and these cells have to describe at the same time the gas phase and the solid phase, and that's in these cells that we have to describe the transfer between the solid phase or the vegetation and the gas phase or the ambient. And so we use physical laws, and we also implement the environmental parameters. So we have to describe the fire triangle, so the fuel, the oxygen, and the heat. And then we have to describe the vegetation properties, which was the aim of another talk by Mike Gallagher. The atmospheric data, the topography, everything has to be basically, we have to throw everything in the pot so our model can apply its recipe and provide a good. Next slide. So I don't want to scare anybody with equations, but basically that's just to show that in every equations, for instance, here in the conservation of mass, which means in a very simple way, the fire is just transforming the mass. The fire is transforming vegetation in gas, and these gas are transformed again from combustion gases to products, which is the smoke. So this whole transformation is happening, but we are not making mass disappear anywhere. It's just transformed. It's moving from the vegetation to the atmosphere, and there are different stages. So in these equations, the first one in the example for the mass balance is for the gas, and the other one is for the fuel. You see that basically the m dot PR, KPR, in the second equation means what's the gases produced by pyrolysis, so by the thermal degradation of the fuel. We have to find them in the gas phase because that's where they go. And the fuel is vaporizing. You find this gas in the gas phase. And we're doing that for all the equations. We say that the energy, which is transforming the flames, a lot is going out in the fire plume and is convected in the atmosphere, and some is getting back to the unburned fuel and is hitting the unburned fuel to spread the fire. So all these what we call interface relationships are very important, and in a way we have an idea of what they look like, but it's very, very difficult to quantify them. And that's where we use the support of experiments to measure the mass loss when the vegetation is burning, to measure the heat transfer, so the exchange of energy, or to measure the wind and the flow, so the exchange of momentum. So that's what we are trying to do with our experiments, is basically to feed the model, explaining how the different phases, the gas phase, so the air, and the solid phase are interacting together. Next slide. And that's a very difficult problem because you cannot very easily separate it. For instance, if you, a lot of the simple models say that the mass you're losing from your fire, you're finding it in the heat transfer. And so you decouple in a way the system by saying, I know exactly how much mass will be lost, so I can infer what the heat transfer will be, because if my flames have this size, the fire will spread this way because it will send that much energy forward to spread the fire. The problem is that, as you can see here, and that's experiments that we did in New Jersey, depending on the type of fire, on the left you have a ground fire, which basically burned everything, and on the right you have the surface fire. And if you're looking at the shrub layer, you can see that on the left, almost all the vegetation is gone. We just see white ash and a few stems of the shrubs and the trunks of the trees. And on the right, you see that quite a lot of the shrubs remain and that the needles are still on the trees. So basically, that's to illustrate the coupling that there is. If you fire burn more intensely, it will consume more vegetation. So if it consumes more vegetation, it will burn more intensely. So there is this really strong coupling that we want to describe because it will make the difference between a surface and a ground fire. And that's in terms of describing the fire behavior, that's very important to know if you will have a surface fire or a ground fire. Next slide. So then we're looking at the experiments that will help us to inform the model. As we cannot describe all the chemical reaction from every single molecule, and we cannot describe all the, for instance, the heat transfer by every soot particle and radiation from the gases in the flame, we have to do assumptions. And usually in our interface relationships, we're using empirical relationships or laws or coefficients. And we have to determine these empirical coefficients from the experiments. And also those experiments allow us to, for the fit scale, for instance, to validate the model. And so basically we simulate a condition and we look at the field experiment and we look if we represent correctly the fire behavior. So the experiments help us at the same time to create the inputs for the model, to create the coefficients for the model, and also to validate the results of the model. And so one of the issues we have with these experiments, if you're looking from the top, if you're looking at the microscopic and the bench laboratory scale, that's where you describe the sign, combustion, and thermal transfer. And that's where you have the maximal control. You can do experiments which are very well designed, very repeatable, and that will give you a very good information. But it's far from the realistic fire behavior. So you're not really taking into account the heterogeneity of vegetation because you are at a too small scale. You're not taking into account the turbulence and the effect of the atmosphere and the effect of the different fuel layers. So basically, you have to move towards scales where you have less control. So that's explaining why you have to do it step by step. And if you're looking at the different steps, basically, one step that we are really missing, and next slide, please, is the scale in between the large-scale laboratory and the small field scale. And that's where really we are missing information. And why? It's because in a lot of the field experiments that we've done in the frame of the different projects we've conducted in the Pine Barrens, but it's also true for other experiments done in the frame of other projects such as Arix Cadre or FASME or the wall experimental fires field experiments done in Australia and in other countries. One of the problems is when you're moving into the field, a lot of the aspects that we are not describing well are linked to the wind. Because the wind is so turbulent in the field, is so unpredictable, and so difficult to measure that we're not capturing that well. And so we don't have the right input for our models. If we don't know well the wind, how can we describe the influence of the wind? So what we decided to do with this wind tunnel, and SK will detail how the wind tunnel is made and what is its purpose, is really to try to fill this gap and this missing link between the basically large scale, which I would call here in the experiment the large bench scale, and the field scale. So we have a wind tunnel that we can use in the lab and in the field, and that allows us to simulate the same conditions with an idealized vegetation in the lab and with a realistic vegetation or real vegetation in the field, and look at what's happening in the process. So that's really where the wind tunnel is located, and this slide basically represents in another way the project that we are conducting. Basically, that every single experiment, because of the different scale involved, allow us to inform the model and to test the model. So if you're looking at the experimental side on the left, and from the bench scale to the field scale, you see that from the bench scale, we can have experiment that we can repeat easily. Easily is, of course, sometimes more wish than anything, but we're trying to, at least we have the much better control conditions. And so when we go into the field, we want to remove this unpredictable aspect of the wind, and so that will make the link between the bench scale, where we control everything, even the layout of vegetation and everything, and the field scale, where we don't control the ambient conditions, the layout of the vegetation, the moisture content in the vegetation, in the soil, and so on, but we control the wind. So that's the missing link. And now I can leave the floor to SK for the rest of the talk. Thank you.
Thanks, Albert, for the introduction. So I take the presentation from now on to talk about more technical stuff, how we built the wind tunnel and what this can do, and how we can fill the gap between the field scale experiments to the laboratory scale experiments. As Albert said, this tunnel has to be used in both laboratory and field experiments. So it has to be large enough to accommodate some real vegetation in the field, but has to be, at the same time, has to be small enough to fit in the laboratory scale. So the wind tunnel it has been designed and constructed and housed in the Fire Protection Engineering Lab at WPI, where we have a 6 by 6 meter large hood in the lab. So that's kind of our limit in terms of the size. So we picked the largest test section area we can accommodate with this hood. That was about the 2 meter by 1.5 meter cross-sectional flow area at the test section. So the size being that big, we cannot design this tunnel as conventional wind tunnel we use for a bunch of mechanical engineering studies or aerospace engineering studies, where we have large cross-sectional area change from the source of the power, which is fan or blower, to the settling chamber to the test section. Typically, in the conventional wind tunnel has large settling chamber with the contraction ratio of 16 to 64 to make the uniform flow, relatively uniform flow at the test section. In other words, if we have a 2 meter by 1.5 meter flow area in the test section, our settling chamber should be in a size of 10 meter by 15 meter, which is not feasible to bring that size to the field. So we took a different approach to use the pressure drop instead of using area change. As you can see at the bottom of this slide, so we basically use the rectangular settling chamber, which has a smaller cross-sectional area than the test section. So basically, we put a lot of perforated plate and the woven wires and honeycombs to uniformly disperse the flow in space, so we can get the relatively uniform velocity profile at the test section. So we have well-controlled wind when we test when we perform the experiments in both laboratory and field scale. So we picked the fan that can power the flow speed up to 6 meters per second with a turbulent intensity around 20%, which is relevant numbers for the most of the forest service research stations. So average speed of those stations are around 3 to 5 meters per second with a turbulent intensity of 20%. So turbulent intensity is the representation of how much fluctuation in the flow we have. So the overall length of the tunnel is about 12 meters, and the test section is half of that. So now we are looking at the ISO view of this tunnel. So we have fans that blow the air from the downstream of the fan to the settling chamber. And as I say earlier, there are a lot of pressure drop, so we can achieve a relatively uniform flow at the axis of this tunnel body. And that uniform flow enters the test section, which it gives a lot of optically accessible windows. So the question to us is then how we can move this tunnel to the actual field test. So we made this tunnel that can be broken into many pieces. So we can bring smaller pieces, many of the smaller pieces to the field, and then assemble those pieces in the field to reconstruct this wind tunnel to blow wind in the field. So basically, the fan can be detached, and the transitional body can be detached, and all the tunnel body can be disassembled like this, and then test section can be disassembled like that. So this is the assembled view of the wind tunnel. We can see the fan at the left-hand side, and then test settling chamber, and in this settling chamber, you can see a lot of lines like this, like that, where we have 14 holes, so we can disconnect this tunnel body into smaller pieces, like one piece there, one piece there. So we can put these pieces into the pallet like this. So all the tunnel body can be broken down into one pallet. All the test section can be broken down into another pallet. So we can, and the fan and the transitional body can come up as well. So we can load all of these into the one mid-scale moving truck, so we can move this wind tunnel to the field. Then we wanted to show what kind of studies we can do with this tunnel in the laboratory. So we did some demonstration in the last year. We put some of yew shrubs and then pine needle little layer in the wind tunnel and ignite it at the front, and then blow the wind from the left to the right like that. So as you can see, there are like a good tilted fire, which is like half of the height of the test section. So it can remain within the envelope of the relatively uniform velocity profile. So we could measure the shape of the flame. We could see the spread rate. We could see the intensity of the flame. So this demonstration shows us this wind tunnel can actually be used to investigate the fire behaviors in laboratories. And so we wanted to improve our wind tunnel, so we started to characterize the flow out of the tunnel by using pitot probe arrays. So we use 7 pitot probes. As you know, these pitot probes measure the stagnation pressure at the tip and the static pressure at the side. So if you take the differences between two pressures, we can extract the speed information like this by using simple Bernoulli equation. So we can do some point measurement like this, and then by moving this pitot probe up and down, we can construct the velocity profile out of this wind tunnel. And this is the some of the results we recently got. So as you can see, we can achieve a relatively uniform flow for lower side of the flow from 1 to 2 meters per second. But as the speed goes up, it sees some non-uniformity. So we plan to install more perforated plates to impose higher pressure drops, so we can achieve more uniform flow or even higher speed of the wind tunnel. So in addition to the pitot probe array measurement, so we can measure the velocity wherever the location it is in the test section. We can measure the mass loss during the burn test. We can measure the temperature. We can measure the heat flux out of the combustion, And thanks to these transparent windows with good IR transmission, we can do a lot of other optical-based diagnostics that we typically use for fluid mechanics studies in mechanical engineering or aerospace engineering. So one example is particle image velocimetry, that we can measure the velocity field, not just the point measurement like a pitot probe. So we can produce a lot more data in much shorter time frame, so we can have the modeling effort as well. So we can also do IR imaging for the heat flux measurement and other spectroscopy type of the optical techniques as well. And the picture from on the bottom of this slide is the exemplary picture of how the PIV measurement is done in this large scale fires. So basically you see the V-shaped fire propagation, and then these researchers used PIV technique to measure the velocity field like this. So what you are seeing on the left bottom picture is the velocity field measured in situ with flame propagation. So to those of you who don't have any background on this type of measurement, I just would like to introduce a little bit more details about PIV, which will be one of the major tools we're gonna use for both laboratory and field experiments, so we can generate more accurate velocity field data, so we can extract the momentum information as well as drag information, which we can feed into the modeling effort. So what particle image velocimetry do is using the scattering light out of the seeding particle. So if you choose seeding particle size for your flow, that particle can follow the motion of the fluid. So if you fire the laser onto the seeding particles, you can basically scatter the light of that particles. So by using scientific camera, you can capture those light. So basically you can take a picture of the locations of the seeding particles like this. So what you are seeing here is one of flow field with a bunch of seeding particles illuminated by the laser. And then you fire another laser at the time of delta T, like here. So now you fire the laser again, and then by using the scientific camera, you capture the location of those particles at different time frame, like this. So from this to there, what you can extract is the displacement of the particles within certain time frame. So by using the cross correlation, you can extract the velocity field. So this can be the powerful technique, especially we have to deal with large scale flow area. So by just using sodium anemometer or pitot probe might be tough to generate the more data. So using PIV would be beneficial in terms of generating accurate data set for the model validation. So before we jump into the real vegetation test, we started to look at more simplified field studies to see what kind of things we actually can do with this tunnel. So what you are seeing here is the Dowel array ignition and flame propagation study done with this wind tunnel. So we basically put a bunch of Dowel arrays like in this picture, and we blow the flow. Now we ignite the first dowel and then see how the flame behave in time. So we placed this array of the dowel at the center of the test section, and this is one of the examples of the flame that we can see from these dowel arrays. So first we look at how the flame spread is done with this dowel. So first we look at the critical spacing, which is the spacing between dowels that jump that make the flame jump from one dowel to another. So for example, at 0 meter per second, where we don't have flow, if you place the dowel at 1 centimeter like this, the flame makes ignition of the next dowel. However, if you put the dowel with 2 centimeter spacing between two, then you are not going to get the flame propagation. Okay, so we subjected this dowel to at different speeds 1 to 3 meters per second, and we look at what's the spacing that gives us the flame spread. And one of the interesting things we found is that this is not linear relation. So, for example, from 0 to 1, 1 to 2, 2 to 3, we have all different behaviors. So from 0 to 1, we have increased spacing. 1 to 2, spacing remains same. 2 to 3, actually the spacing decreases. So what I want to say with this is that by using this tunnel and simplify the study, we can actually tell there are some interesting chemical, physical behavior going on. So we cannot simply use the constant coefficient for every single speed that we use. There should be certain regimes over the speed or whatever variables we are using that gives us different behaviors like that. So this is one of the demonstrations that this wind tunnel can actually help to improve the modeling effort. So at the same time, we measure this flame spread as well. So we measure the spread rate by taking 2 spacing, 0.5 and 1 spacing. We measure the time to ignition of each dowel. So for example, in this plot, so the second dowel, which is noted as dowel 1, was ignited at time of 5 after the ignition of the leading edge dowel. So for example, the next dowel was ignited between 5 to 10 seconds. So if you take the regression field, we can extract the spread rate. So this is the result. And once again, one interesting finding we observed was the behavior of fire spread differ condition by condition, and there will be we suspected that there are like interesting chemical and physical phenomena going on for each specific conditions. So we try to explain this behavior by using some flow chemical coupling, by using wakes and entrainment. So I don't want to go too much in details about that, but what we found is that when we calculate something, even these simple things, we cannot rely on the certain assumptions. For example, if we assume the constant temperature for the flame, the modeling result will be suffered because the temperature of the flame will differ depending on the characteristic structure of the wake that we observe with this simplified dowel. So again, with this wind tunnel, what we can do is we can actually look into more fundamental side, so we can tell the simulation tool to improve in certain circumstances, for certain circumstances. So another thing we tested was measuring the momentum by measuring velocity field. So this one was done without reaction. So we just used the pitot probe arrays instead of PIB, because currently we are trying to implementing the PIB technique to the wind tunnel now. So the velocity measurement technique we have now is just the pitot probe array. So what we can do by using velocity field is that we can measure how much momentum is going into the region of interest and how much momentum is going out from the region of interest. So we can calculate the drag associated with the presence of the obstacles like this dowel. So all these momentum in and momentum out and then drag measurement can be done by measuring velocity field. So the PIB can be again a powerful tool because it can provide more information to the simulation tools. So this is one example. At different speed, we don't get too much drag, but at certain conditions we can get like a much drag, just like that. So next, we started to look at actual vegetation tests. So we started to repeat what we have done with the dowel arrays with real, I should not say real, but the more realistic vegetation configurations. So a couple of things we have done is we tested the shrub and pine needle structures, and we tested the shrub, pine needle, and branches structures, and we are measuring the velocity field upstream and downstream of the vegetations, and we are scanning the structure of the vegetation using LiDAR scanning. Like I stole this from Mike's presentation, so like Mike presented us the other day, so we can use LiDAR scanning to construct the structure of the whatever vegetation we use here, that we can feed those information into the modeling, and we also can provide all other associated measurement quantities like velocity field, like temperature field, the heat flux out of the combustion, and so on to the modeling, so we can improve the result of the modeling. So this slide simply shows the steps of model validation. So we did some tests with more realistic vegetations. We scan all the structures, and we measure all relevant properties like velocity field, temperature field, momentum, and other quantities of interest, and we burn those vegetations. It can be either back or the spreading or forward spreading. We can measure the speed of the spread, shape of the fire, and the heat flux out of that fire as well. And then we rescan with LiDAR to scan the structures after burn, and we can feed all of the data obtained throughout this process to the modeling, so we can validate the modeling and tell the simulation to look at more specific scenarios like I showed you with the dowel arrays. So let's get back to this slide. So what we do with this tunnel is bridging the gap between small-scale laboratory experiment and then small-scale field experiments, so we can help to improve the numerical modeling. So eventual goal of this project is bringing this wind tunnel into actual forest like that, so we can control the wind, so we can provide more controlled experiments with leading edge, with accurate measurement of relevant quantities like the velocity field and then temperature field and so on. So we can improve the modeling in the future, which can aid the fire measurement in the future. Okay, so I think that's all for the technical part, and I hand this to Albert so he can summarize and give us some more guidance for the future work. Thank you.
Thank you, SK. Next slide.
So I this is the conclusion slide you gave me.
Okay. Yes, which I don't see, so I will put it on my screen. So basically, one of the big steps for the use of the tunnel and beyond what SK described about what we have already started and that we will continue is to test the wind tunnel in the open. So the idea is by the end of this year, and as we are in New England, basically before it's too cold, is to assemble the tunnel outside and see how we do it, because that's still, even if it's pretty portable and can be basically put on 2 pallets plus the fans, it's still a difficult task, and we've never done it in the field. And also, one of the ideas, if you want to do a series of experiments in the field, is to be able to move it from one prepared plot to the other. So we'll see how we can move it without dismantling it totally. So that's more like a trial kind of step to see what we can do in the field. We want also to add measurement techniques, and so SK mentioned the particle image velocimetry, and one of the issue with this PIV is the particles that we're seeing, and in a lab setting it can accumulate pretty fast, and some of these particles are not very nice to breathe. So being in the open will help us to not face this specific problem. So we want to test different vegetation configurations, and you've seen some part of that. The important thing is to try to move from something which was well characterized in the past, like pine needle leaders, where you have a wealth of experiments from Missoula to several labs in Europe, Australia, and even China, and compare our results to the existing and move towards vegetation configurations which are more representative of what we find in the field, and especially in the pine barrens, because that's where we are doing our small-scale experiments. And then the other two aspects are actually to conduct the field experiments. So there are two types of field experiments, as the CFD models that are presented are three-dimensional, and one of the big aspects of this and specificity of these models is that they can represent the 3D flow, around and inside the fire. We want to start to do some experiments in cold flow to basically see if our modeling of the interaction of the wind and vegetation is correct, and maybe to improve it. And then the last step would be to conduct fire spread experiments with actual fuel in the field, and then compare that to what we could build in the lab with our representation of the actual fuels, and really look at how we did bridge this gap and where we stand in this regard. So that's it, and after that I want to thank the audience. Thank you very much.
Thank you, and if you have any further questions, or we not take questions, but if you have any questions or inquiries, you can simply send us an email so we can reply you back. So thanks for your attention.
Yeah, guys, that was great. I mean, given what I see of the audience here, I think that was probably right up the alley for what most of us were looking for from you two. We're just about here at the end. Xander, do you have time for one question, maybe?
Sure.
Okay, does anybody, if we have one, I mean, it might be better to just shoot these guys an email, but does anybody have a question right now? I'm not as good at imploring people to get questions as Amanda, but maybe that's okay for today. She's not on, so she won't know. So, okay, well, hey, I really appreciate everybody signing in and listening. Albert and SK, that was awesome. And Xander, thank you for facilitating this again. And thanks to everybody that was along for the ride today. I think we'll do another one of these in 2 weeks. So thanks, everybody.
Thank you.
Thank you. Goodbye.
Thank you. Bye.